chapter 14 homework. Go back over that real quick. Okay, resonance structures. Number one, you have this CH2. Yeah, this compound, you can move the double bond here to the plus charge, and that will produce this compound. And then you can use the lone pair on the oxygen to share into that plus charge. So there's another resonance structure you can draw, which is actually a diene that has a positively charged oxygen. Just one. This particular question asks for all of them. So when you have a plus charge, that's where you're moving toward. You're moving to the plus charge with the electrons. It's always electrons toward the plus. We got it down? Okay. The next one is an intermediate in the electrophilic aromatic substitution reaction. So you have one sp3 carbon in the ring, so it's not a benzene ring. So you can move this double bond here. Whoops. Here, and here is where that one we didn't touch. The plus charge is now going to be here. And then we can move it again and have another resonance structure with the plus charge next to the OH. And then the OH can share in its lone pair. So there's another one. 4 resonance structures where the oxygen actually can take up the plus charge onto itself. So again, we're moving toward the plus charge. Okay. Now the third one has a negative charge. When you have a negative charge, that's where you begin. And we move it. The only place we can is there, and then open up that pi bond. And that makes a conjugated system. So this is a very stable resonance structure because it's got a diene in it. And then you can go back to the other side. You can close this back, move this here, and open that there, and that puts the O- on the other side, which is an identical resonance structure to the first one, just flipped over, but the two of them make this a very stable entity, and the fact that it's a diene makes it very stable compared to this one. All right, number 2 has you ranking these compounds in terms of stability, with 1 being the most stable. I have to draw these kind of small. I've got 2 double bonds, 2 double bonds. Oh, they're not 4. Okay. And 3 double bonds in a row. So 3 is the best. That's a benzene ring. So that's the best when you have a benzene ring. And then which one is 2? Yeah, it's got them conjugated. And here they're isolated. And then I've got 2 double bonds in conjugation, 3 double bonds in conjugation, 2 double bonds isolated, which is number 1. 2. Second one, then the first one, and then the isolated ones are last in stability. Conjugated diene. It's an adjective of a diene. This is an isolated diene here. All right. Reactions. We got butadiene and HBr minus 78. So you put in your charges and bond your C1 to the H, and C2 becomes the plus charge. Has to be allylic to the double bond. It has to be next to the double bond. It can't be isolated from the double bond. And then at minus 78, the Br minus bonds to C2, and you get 1,2 addition. We don't use the other double bond at all. It's like it wasn't even there. B, we're doing the same reaction, this time with HI at 50 degrees C. So again, C1 gets the proton, C2 becomes a carbocation, but at 50 degrees, the other carbocation, the resonance structure, prevails, so that you have this resonance structure prevailing at 50 degrees. And then the I minus bonds to C4. And so you end up with an I, and then your 4 carbons. Okay, make sure you still have 4 carbons in your product. Don't turn your 4th carbon into an I. That's 1,4 addition. Now C, it doesn't matter what the temperature is. When you have cyclopentadiene, you bond C1 to the proton, and C2 again becomes the carbocation. And again, it has to be allylic to the double bond. That's the stable intermediate. And the resonance structure that you can draw for this is identical to it. So the Cl minus bonds there or there, doesn't make any difference. You get the same product. You get this. Okay, furan and the triple bonded compound. So you have to draw it sideways so that your double bonds are facing the alkene, or it's actually a triple bond here, dicyano. And so we're dotting the end of the diene to the end of the ene and drawing in our arrows. 1, 2, 3. We're going to have a double bond on the left and a TP with an oxygen at the top. And we're going to have a double bond on the right in our cyanides. And those are sp2 carbons, so there's no up or down. Okay, then we have 1,3-butadiene, which we're going to draw this way, and cis-1,2-dibromoethene. And again, we're dotting the ends to the ends, drawing in our arrows. This time we do not have a bridgehead. We're just making cyclohexene, and our bromines, which were cis, remain cis due to the retention of stereochemistry. No, this is 1,3-butadiene. They're both 1,3-butadiene. There's no cis or trans. It's just drawn a different way. We're just rotating the central bond so that it becomes that. That's all we're doing. But it has to be in that conformation to do the reaction. So that's why the rings work better, because they tie those double bonds into that conformation. That's your reagent, the heat. Cyclopentadiene, again, we've got to draw the double bonds facing the alkene. And maleic anhydride, this is the one you did in lab. So again, dot the ends together, and then draw in your arrows for your electron motion, and we're forming a bridgehead, double bond, bridgehead, and then endo and cis. Yes, if you don't have a bridgehead. Okay. We did a lot of these in class before. Draw the starting materials. I've got down bromine and an up bromine, so they are trans. And this comes from, start with your double bond, and we're going to move it here. We're going to break this bond and move it here. We're going to break this bond and move it here. We're just going backwards with our arrows to make this and the trans double bond compound. B has a bridgehead with an oxygen at the top. Oh, we just made this compound. So it's from furan. And the triple bonded alkyne, the alkyne. Put the cyanides on it. And then this one we did in class as well. Again, we're just moving this double bond. That's it. And so that comes from cyclopentadiene and norbornadiene, which is the name of this compound. Okay, so we're good with chapter 15? It's backwards from the Diels-Alder reaction, going back. So this double bond goes here, that's here. This double bond goes here, that's here. That breaks the bond between them. This breaks the bond between the two entities here and forms a double bond here. Same. Here, here, here. Yes. No. Just draw the products. I mean, the starting materials. Okay, so chapter 15, we're okay? All right. So let's go to 16. Ranking. Let's just do a couple of these. We did not have acid analyte in class, so, well, it's not on there anyway. Okay, so this is chapter 16 homework. Number 1, you've got benzonitrile, phenol, chlorobenzene. This is just a shorthand for benzene ring. It's a phe, and styrene, which is number 1. Phenol, and number 2, styrene, and then the chloride, and then the cyanide. Okay? Any questions about that? That's the benzene ring. It's a phe, which sometimes is pH, if it's typed, or phenyl. All those stand for a benzene ring. That's a substituent. So you can draw it in like that. If you're not working with it, you can just use that. If you don't have 2 substituents on it, you can use that. Okay, so we have an I, a benzoic acid, nitrobenzene, and aniline. What's number 1? Aniline, nitro is 4. What's number 2? Yeah, yeah. And then the COOH is third here. Okay, let's get to the reactions. Okay, number 2A. Toluene and NBS. Yeah, and there is only one benzylic carbon here, so it replaces one of the benzylic hydrogens with a bromine. There's no such thing as 2 benzylic carbons, unless you have 2 substituents on the ring. Isopropylbenzene and CaMNO4, hot CaMNO4, makes benzoic acid. dehydration reaction. We have, OH. H plus, the lone pair bonds to the proton, forming water. Which breaks off to form the benzylic carbocation. And then minus H plus, that comes from this hydrogen over here, donating its electrons to the carbocation, and we form a double bond to that other carbon. All right, G, I'll just leave that bottom part up there. D is benzoic acid, and now I need to draw in my bonds, and we're reacting that with SO3H2SO4, so that makes SO3H plus, with the plus on the sulfur, and it's a meta-director. COOH is a meta-director, so we're going to put the SO3H on the meta-carbon. Yes, Camera? No, but I'm doing all the mechanisms. Okay, so we're putting the SO3H on the meta-carbon. The para-carbon is plus. You have to have, if this is net plus, everything from there on has to be net plus. And the electrons from the hydrogen's bond are given to the carbocation, and that reforms the benzene ring. And you now have an SO3H on the meta-carbon. Any questions? All right. E. We have toluene and 2-propyl chloride in AlCl3 makes this secondary carbocation. And methyl is an OP director. So we're going to go to the para-carbon. Just pick one and put it either O or P. And I'm choosing para. So I'm putting my isopropyl group on the para-carbon. Sorry. My plus charge is on the meta-carbon. My para-carbon is now sp3, and the H donates its electrons, getting itself kicked out with no electrons, and that re-aromatizes the ring, and we get this. Okay. All right. F, we've got acetophenone, which is this compound, methylacetyl rather, and we're treating this with HCl and zinc mercury. That is called the Clemmensen reduction, and it converts the carbonyl into a CH2 group. So instead of a carbonyl, we now have a CH2. No mechanism for that. FG. What is going on? G. Nitrobenzene and FeHCl. That turns a nitro into an amino group. Okay, and then we have benzene itself reacting with the compound that you get when you take the bromine off benzyl bromide, which is another name for bromomethylbenzene. Anyway, you take the bromine off, form a carbocation there, and then have your benzene bond to it. Doesn't matter where, because on benzene there's no directing group. So we're going to put a plus charge there, and our CH2 and another benzene ring here, and there's a hydrogen also on that carbon. And the hydrogen gives up its electrons to the carbocation. Reforming the benzene ring. And you get this compound. This is not a primary carbocation. This is a benzylic carbocation. So it is even more stable, or about as stable as a tertiary. So it's a very stable carbocation because that plus charge resonates into the ring. Okay, we got phenol. Phenol and the T-butyl bromide and AlBr3 makes the T-butyl cation, the tertiary cation, and OH is an OP director, so we're going to put this para, and you bond to the tertiary carbon at the para carbon. Puts the plus charge over here, and now we have a T-butyl group attached. And then minus H plus gives you your benzene ring back and it's got an OH on it and a T-butyl group in the para position, because that's where I chose to put it. And again, this para carbon. Okay, stop me if you have questions. J, biphenyl. We're using one of the benzene rings, and the other one is our directing group, so you can just do that. And NO2 plus is our electrophile. Phenyl is an OP director again, so we're going to go to the para carbon. Plus on the metacarbon, and we have another benzene ring up here. And then minus H plus. Puts a nitro group on the para carbon to the other phenyl ring. Yeah. Doesn't matter. Just don't do both. Just one. Okay, benzonitrile. Okay, benzonitrile has the benzene ring with a CN, a nitrile group, and that's a meta director. And we are adding Br+. So again, use the double bond on the carbon that we're interested in. We're putting that bromine meta. Putting it here. Plus charges on the para carbon. And minus H plus. And this is the arrow that shows that happening. Reforms the benzene ring, and we have a bromine on the meta carbon. Okay, L. L is anisole. Anisole is OCH3, and that's an OP director, and we are bonding to it this electrophile, the acyl cation. I'm going to just put it ortho for a change. And then, whoops, I don't have too many bonds in there. The plus charge will be at the next door carbon. We have our H, and then we have our acyl group, and then minus H plus. Gives us a benzene ring for our product, and we have this carbonyl attached to that's another benzene. That's a benzene, a phenyl. It's typed there as pH. but stands for phenyl, which is a benzene ring, which is that symbol, Phe. Right. Just pick one. Okay, L. What I got? Oh, that was it. Okay. Synthesis. Para-ethyl bromobenzene. That means you have bromobenzene, that's your parent, that's carbon number 1, and para, you have an ethyl. You look for the parent name, that gives you carbon number 1, and then you know where to put the other substituent. Tamara? You don't have to do any mechanism in synthesis. I don't want any mechanism in synthesis. Just the reagents on the arrows. No. From benzene. Okay. How do you put an ethyl group on? We're making this compound from benzene. It says para-ethyl bromobenzene is the compound we're trying to make. We're going to put the acyl on first. That's how you put an ethyl on. So we'll have our acyl here. Whoops, wrong carbon. Our acyl here. And then turn that into an ethyl. That's a para director. And then bromine and FeBr3 to put on the bromine para. Yeah. Doing a Friedel-Crafts on benzene, that's fine. You have to do the Friedel-Crafts. Bromine is a deactivator. You don't want to put the bromine on first because it's a deactivator. It's not going to give you good yields. But I wouldn't count it wrong. It's just kind of little details. But it's not as good to put the bromine on first. You can't do a Friedel-Crafts on metadirectors or aniline. That's a major limitation. I started with benzene. I can do a Friedel-Crafts on benzene. It's not a metadirector there. Tells you where the ethyl is. Para-ethyl. Bromobenzene is the parent name. Ethyl is on the para carbon. Got it? It's the compound you're making. You're making this from benzene or toluene or whatever. But you're synthesizing this compound. This is metabromobenzoic acid. So we have benzoic acid is our parent, metabromo is the substituent from benzene. So what are we going to do? We have to put some kind of group on there that we can turn into a COOH. It's not going to be a primary group or a second, or it has to be secondary, or well, it has to be secondary. No, all you have to do is this. With the chlorine there and AlCl3, we'll put an isopropyl on your ring. And then you can turn that into COOH. That's the easiest compound to put on, the easiest group to put on the ring to turn into a COOH is an isopropyl. And that's a meta director, so we're going to do bromine FeBr3, and that'll put our bromine on meta. But that's how you get a COOH on the ring. If you already have a methyl there, then you could just turn that into a COOH if you needed to, if you starting with toluene. If we were starting with toluene, this would have been a two-step synthesis. Because I told you, don't do that. Don't use a primary group. That doesn't work. It doesn't work. No primaries. No primary halides. Okay. T-butyl nitrobenzene. So we have a nitro here, and on the paracarbon, we have a T-butyl. And again, from benzene. Mm-hmm. Yeah, this looks like a two-stepper, doesn't it? Put the T-butyl on, and then the nitro. No mechanisms here, please. Just, there's not enough room on the paper for all that. Just the reagents. Okay, so that's a two-stepper, and then the last one is quite long. Sure. All right. Styrene and meta nitro. From benzene. Meta nitro styrene. Well, that's the problem. You turn it into an ethyl, or an AC. The way you put a two-carbon group on the ring is to do an acylation. And that is a meta-director. Now you put your nitro group on. So you have your meta director, you have your nitro now. Now we're going to reduce, but we have to use iron and HCl because we do not want to reduce the nitro group. Oh, sorry, wrong one. That's the nitro reduction. We want to do, N2H4 and KOH. The Wolff-Kishner, that'll turn that into an ethyl. And now we have an ethyl there. Looks a little strange. Okay. NBS introduces a functional group right there on the benzylic carbon, and then T-butoxide to do the E2 reaction, and that'll give you the double bond. So 1, 2, 3, 5 steps. I'm not going to give you one that long, but T-butoxide, E2 reaction. Yeah, Clemenson will work as well as the Wolff-Kishner. Right, it'll reduce the nitro as well. Yeah. Yes. Don't know. I haven't made it up yet, but I don't think so. Yeah. No, you do the nitration in between. Name like that. Yep, just like that. I'm sorry. The E2 reaction. If you don't know your E2 reaction, you need to go back and review. No, you wouldn't start with toluene then. There's no way to get rid of the methyl. Yeah, you start with toluene if you need to turn it into a COOH. Yeah, it's easier to just, instead of putting an isopropyl on and then turning that into a COOH, you can just start with toluene and save the step. Okay, where would the third electrophile go if you have two rings and these are connected by what's called an amide bond? One of those rings is activated compared to the other. This ring has a nitrogen on it. This ring has a carbonyl attached to it. Which ring is activated? The NH. The NH is an activator. So this ring is activated. And this ring is deactivated. Activated means it's going to do the reaction faster. So then the question becomes, what kind of director is the nitrogen? That's an OP director. So the positions that are available for an electrophile are the ortho positions and the para position. So that's the answer. You draw the arrows to the ring that is more activated and the positions that are the most activated. Okay, so this one's got a methoxy group on it, and then a carbonyl. So which ring is activated? The left ring is activated. This ring is activated. Which positions on that ring? Yeah, pair is taken though, so just ortho. So you point to the ortho carbons. Okay. Anything from the old tests that I've given you that you want worked? Synthesis? All right. Benzoic acid is the parent name. 3-nitro-5-bromo. Because there are more than two substituents, you can't use meta and ortho and para anymore. You have to use the numbers with the parent giving you the position carbon number 1. Okay, from toluene. Okay, so we're starting with toluene, which is an OP director, and we want our group's meta. So what do we have to do first? Change that toluene to a COOH with hot TMNO4. And then you can do the bromination or the nitration in any order. It doesn't really matter. The bromination can be done next. And that'll put your bromine on meta. And then nitration. And that'll put your... Might be good to put the nitro group on first, because then you got two meta directors, and you're not going to get your bromo and any weird ortho effects coming from the bromo. But I don't know if it matter much. Anything else from that exam? Oh, the second one. Okay, yeah. The benzene sulfonic. 3-amino. From benzene. So what are you going to put on first? Yeah, SO3 and H2SO4 puts on the sulfonic acid group. Then what? Nitro and sulfuric will put on the nitro group meta. Then what? HClFe will reduce the nitro. I don't think H2PD is going to touch the sulfonic acid, but I'm not absolutely certain. I don't think it would. So I think you could use H2PD here as well. So 3 steps is standard for me. I like the three-step synthesis. I think, if you can do a three-step synthesis, you're in pretty good shape. And this is a three-stepper. What else? I've already given you two. Yeah, I did one in class, and I gave you one, so there are two. What about the one, meta to each other? Anything else? Hang on, let the camera finish. Yeah, we did that at the beginning of this one, too. The plus charge on the oxygen's got 3 bonds. It's not on the carbon. The carbon's already got 4 bonds. It's not going anywhere. No, that won't be on there. Acetanilide is actually number 1. It's number 1. It's in the top group with anilide and... Yeah, acetanilide is this compound. It's an NH and then a carbonyl and then a methyl. So that's acetanilide. So that's in the first group. Oh, the same kind of deal? Sure. Yeah. Or if there's only one ring, which is the most activated position or positions. Which ring is activated here? Yeah, the OH is activating that ring, and which positions are available? Just the ortho. Paris taken. Okay, then I've got a methyl, number 4 on that exam I gave out last week. Ortho and para to the CH3, which would also be meta to the SO3H. So they kind of reinforce each other there. Those are the most reactive positions. And then again, I have a 1-ring compound. I've got a CH3O and COOH at the para position. Ortho to the CH3O. Number 8, just 2 more examples of that. Oh, another synthesis. Okay, both of them from toluene. Okay, so we've got from toluene. This is that fall 15 test that I posted. Synthesis on there. Okay, so we're starting with toluene. What are you doing to it? First. Yeah, but we might as well just go ahead and put our nitro on because we need that nitro para. So let's just go ahead and do that and then deal with our methyl. What do we need to turn it into a CH2Br? NBS. NBS replaces a benzylic hydrogen with a bromine. And then we need to replace that bromine with an OCH3. So how do we do that? Yeah, with OCH3 minus. Just does an SN2 reaction. We're going to be doing a bunch of SN2 reactions this semester, so that's a real important reaction. Okay, we got a COOH, and then we have an acyl down here from toluene in 2 steps. What do we do first? Yeah, we're going to do the Friedel-Crafts first. Put our acyl group on first. And then what? KMNO4. That'll do it. I mean, that one. Yeah. Mhm. Hang on, I gotta find it here. Oh, I got it. Which one? B? It's not a ring. It doesn't matter. You're counting the pi bonds. There's 6 electrons in pi bonds. There is a lone pair on the end, but it's in an sp2 orbital. It's not in a p orbital. Alrighty. Okay, then I'm going to stop there. If anybody needs a copy of that test, I've got a couple of those if you weren't here. Yeah, here's a copy of that. No, is there something else with that? Sauna. Is there something? Is that the whole? Okay, all right. Put the acyl group on, reduce it. That makes it a para-director. I'm sorry. Second. Oh, yeah. Acyl, then the nitro. Meta. Yeah, the meta. And then reduce this and then do these other, put on the bromine and then get rid of the bromine, make a double bond. Yeah, that's what I asked for. That's what I asked for. It's meta. You have drawn it wrong. It's supposed to be meta. This is representing the compound I want you to make. That's all. Yeah, just like when you have a T-butyl or isopropyl, the chlorine comes off with this and makes the carbocation. Sure, why not? That's a meta, and that's a meta, so this is meta to both of them. You have to look at both of them's directing ability, yes.